Hello students. So last class we discussed about various types of cubic lattices. I think all of you thorough with those topics. Okay, that class itself I told you that was a very important topic and lots of questions are asked based on that. So I think all you thorough with those things. Okay. So last class what we discussed, the number of particles per unit cell in the various types of cubic lattices, isn't it? Okay. So today we are going for a new topic, that is close packing in crystalline solids. Okay. Let's move to our topic. So we have different types of close packing in solids. Now we are discussing about what crystals, that is crystalline solids, right? So in crystalline solids, particles are, while arranging the particle, we have to arrange the particle more closer. More closer means we will have the more stability. So while arranging the particles, what is particle? Constituent particles. I told you many times. What are the constituent particles? Maybe atoms, molecules, ions. Okay. Whatever may be the constituent particles, the particle should be arranged more closer. Then only the structure will be more stable. Okay. So now we have to assume a shape for the particle. Okay. So more closer ആയിട്ട് നമുക്ക് particles കിട്ടണമെങ്കിൽ we have to assume a perfect shape for the particle. Okay. For our convenience, we are considering the particles may be in the shape of spheres. എങ്ങനെയുള്ള spheres? The rigid spheres, incompressible rigid spheres. So now we are considering the particle as in the form of incompressible rigid spheres with equal sizes. Okay, then only the arrangement of packing will be more efficient or more correct. Okay, so we are considering the particles are in the form of rigid and incompressible equal size spheres. Okay, now so that is why we are moving to close packing. So particle should be more closer, then only the stability will increase. Okay, so we have different types of close packing in solids. Generally, first one is one-dimensional close packing. What is that? One-dimensional close packing. So, in one-dimensional close packing, what is that? We know in one dimension we need only one basis vector. Okay, so the spheres are arranged in a linear manner, only in one dimension. Okay, that is already told you particles are in the form of spheres, yes, equal size spheres. So when I drawing the figure, the size of the sphere may be vary, but actually you know that the spheres are in equal size, right? While drawing it will be uneven in size, that you don't mind. Okay, so so spheres are arranged in a linearly manner in one dimensional packing, close packing, isn't it? Okay. So next is the second type is two-dimensional close packing. What is that? Two-dimensional close packing. Two-dimension means the spheres are arranged linearly in a number of rows. Number of rows. Okay. So we have infinite number of rows like this. I can draw this only in this board. That's why I draw only 3 rows here, isn't it? So suppose I am taking this as A type row, this is also the same type row, this is also the same type, isn't it? That is the second row is coming just below the first row and third row just below the second, and like that this packing is going on. Oh, okay. So when you consider the center sphere, any of the sphere, when you consider, we have 4 neighboring spheres around this. Can you see this? Direct attach ചെയ്തിട്ട് ഈ sphere directly attach ചെയ്തിട്ട് how many spheres we have? Yes, we have 4 neighboring spheres here. So you know what is coordination number and all. Last class I told you coordination number means the number of neighboring particles around the central sphere. That is what we call coordination number. Yes. So here the coordination number is 4. Here coordination number is 4. Isn't it? Yes. So the number of constituent particles here it is 4. When you join the centers of these neighboring sphere, we will get a square like structure. So that is why this type of packing is called square close packing. Square close packing. Okay, and in this particular type of packing, you can see many of the vacant spaces here, isn't it? Yes, you know, already I told you vacant space means what we call for vacant space? Yes, voids. Okay, so voids or sites, interstitial sites or interstitial voids we can call. So lots of voids we can see here. Okay, so what is the type of void present here? While taking, we can see number of voids in this structure. So this is the structure we call square close packing. Here what about the coordination number? Coordination number is equal to 4. In two-dimensional close packing, we have another type of packing, right? So in two-dimensional close packing, I told you this is otherwise known as, the first one is otherwise known as square close packing. And here the efficiency or number or percentage of space filled will be 50.4% only. So we can say that is the packing efficiency here. On seeing the structure itself, you can see that lots of vacant spaces are there. So lots of vacant spaces means only few places are seriously filled. Okay, so only the filled percentage is 50.4% only. Okay, so that is what we call packing efficiency, that is equal to 50.4% here, and here the coordination number is 4. And when you join the neighbors of these constituent means the neighbors, the center of the neighbors, when you join, you can you can see a square like structure. That is why it is known as square close packing. Okay, in two-dimensional close packing, we have one more type, that is this one. So here we can call it as AAA type, that is square close packing. Similar rows are repeating here, so AAA type. Okay, so in hexagonal, so the second type of close packing is hexagonal close packing. Why it is called hexagonal close packing? So we will check. So the first row is like this, and the second row is drawn in between the spheres. അതായത് നമ്മുടെ ഫസ്റ്റ് റോയിലെ സ്ഫിയേഴ്സ്, രണ്ട് സ്ഫിയേഴ്സിൻ്റെ ഇടയ്ക്കുള്ള ഒരു വോയിഡ് ഉണ്ട്. ആ വോയിഡിലാണ് നമ്മൾ സെക്കൻഡ് റോ അറേഞ്ച് ചെയ്തിരിക്കുന്നത്. തേർഡ് റോ വിൽ ബി ദ repetition of the first row, like the pattern is arranging in this type of close packing. Okay, so A type row, then B type row, then again A type, B type. So this type is close packing is also known as AB type. Earlier we told in square close packing we have AAA type packing. So here AB type packing. Why it is so? Because first row and second row is different from the first, and third row again the repetition of the first row. So then what about the coordination number here? You just consider the central sphere here, and the number of neighboring sphere. When you count the number of neighboring spheres, you can see that we have 1, 2, 3, 4, 5, 6. 6 spheres are there. That means the neighboring sphere, the number of neighboring spheres for a particular sphere is equal to 6. That is what we call the coordination number. So here the coordination number is equal to 6. So when you join the centers of this neighboring sphere, what you will see? Okay, so this is the shape of a hexagon. So you will get a hexagon while joining the centers of the neighboring spheres. So that is why this type of close packing is known as hexagonal close packing. Okay, so in hexagonal close packing, the coordination number is 6, and it is also known as AB type. In two-dimensional, this is also known as AB type. Here what about the packing efficiency? നമ്മുടെ നേരത്തെ സ്ക്വയർ പാക്കിങ്ങിനെ പോലെ അത്രയും വോയിഡ്സ് ഉണ്ടാവില്ല, ബിക്കോസ് വി അറേഞ്ച്ഡ് ദ സെക്കൻഡ് റോ ഇൻ ദ ഫോം ഓഫ് ബൈ ഫില്ലിംഗ് ദ void gap. So that's why the vacant spaces will reduce compared to square close packing. And here the packing efficiency is 60.4%. Compared to that, this is more economic. Economic means while arranging the particle we have to consider that maximum space will be packed. That's the way we have to arrange the constituent particle. So, comparing this square close packing and hexagonal close packing, which is more economic, by seeing itself you can see that the hexagonal close packing is more economic because it is more filled. So, here the packing efficiency will be 60.4% and the coordination number is 6. Okay. So, in hexagonal close packing I told you we have number of voids. Okay. So, in see this structure, look at this structure, we have AB type row, right? In between this, the spheres are arranged like this. So, while seeing this structure we can see that in between these 3 spheres there is a void present, and in between these 3 spheres here also a void present. That void is I redraw here. For understanding I redraw that one here. Okay. So, in hexagonal close packing we have a void here, and this void is formed by means of 3 spheres, by joining the 3 spheres. While joining the centers of these sphere we will get the corners of an equilateral triangle, isn't it? Yes, this is an equilateral triangle, you know. So, while joining these 3 centers of these spheres, we will get a shape like an equilateral triangle. Okay. So, that is why this void we can call it as triangular void. What is that? Triangular void. So, see, triangular void is present in 2-dimensional close packing of, that is in 2-dimensional close packing, that is more correctly in 2-dimensional hexagonal close packing. 2-dimensional hexagonal close packing, the void present is triangular void. Okay. So, next we move on to the next type of close packing. What is that? Yes, 3-dimensional close packing. In 2-dimensional we have square close packing and hexagonal, isn't it? That is AA type, AB type. So, now we move on to the 3-dimensional close packing. 3-dimensional close packing, first type is same, that is the first row is we can draw a spheres in a line. So, the second row is just below the first row. Third, this is the basic layer. So, keep in mind this is 3-dimensional. So, we have number of layers above this or below this, okay, because this is a 3-dimensional packing, isn't it? Yes. So, number of rows are coming. So, next, what about the next row? This is second layer. What about the second layer? The second layer is also just above the first layer. Okay. All the spheres are just above the first layer. Such type of, so here the second layer will be like this. Same type of layers are forming in this type of close packing. This is the first type in 3-dimensional close packing. Such type of close packing is called simple cubic close packing. Okay. So, here the possibility of seeing more number of vacant spaces or voids, isn't it? So, lots of the space will be empty. So, formation of voids will be more. So, here what about the packing efficiency? It is only 52%. Okay. So, what about coordination number? In the first layer, it is when you consider the central sphere, any central sphere, in the first layer itself you can see that there is 4 neighboring spheres. Okay. So, like that the above, below, okay, and down. Okay. So, 4 neighboring spheres, above etra undavum 4 vatto illa. Because above idhe layer arrange cheyumbo namukku 1 above and 1 below undavum. You have to imagine the 3D structure of this. Okay. So, 4 in the same layer and 1 above, 1 below. So, total number of neighboring particles will be 6. So, here the coordination number is 6. Okay. So, the first type was simple cubic in 3 dimension. Okay. So, then second type in simple cubic you see that in 2 dimensional we have the square close packing, that was the base in simple cubic 3D, and base will be the square close packing itself, then we are arranging the layers just above and below. That is what we seen in simple cubic close packing in 3D. Then next 3D arrangement is this type. So, this is what in 2D we said that this is an hexagonal close packing. So, the layer is forming above the hexagonal close packing will be the second type in 3 dimension. Okay. So, I told you here we can see 2 types of voids present here, that is the type 1A. Here you can see a void present, and type 2 void, B void is also there. So, A type void, B type void. In the first layer itself we can see that we have 2 types of void, A type and B type void. So, while filling the second layer we have 2 possibilities. Which are they? Yes, covering the A type void, either you have to cover the A type void or you have to cover the B type void, isn't it? Covering this 2 type void at one time is possible? No, it is not possible. Seeing itself you can see that it is impossible. So, you have to cover either A void or the B void. Suppose we are covering the A type void. So, the second layer I can represent like this dotted line. Okay. So, you represent like this dotted line. This dotted line is the second layer. Okay. This is a 2-dimensional board. So, I can only represent like this only. So, you have to imagine the more in 3D view. Okay. So, I am filling this A type void. So, the second layer will be formed like this. Yes, here also one A type void, and like this the second layer will be formed. Okay. In the second layer also, the next layer will be you can't fill this or cover this B void. Next A type void we have to cover. Okay, in between these spheres, like this the structure will be coming. Okay. So, in the second layer also you have 2 types of voids, CD. Suppose it will be, we can name it as CD void. Okay. In the first layer we have AB void, and the second layer we have CD void. Okay. Then while arranging the third layer we have infinite number of rows here. Okay. The first infinite number of layers. Okay. So, first layer is just same as that of hexagonal close packing in 2D. Then second layer we filled the A type void we covered. Okay. So, in the third, while filling the third layer also we have 2 possibilities, which are the C or D. So, we have, while we filling the C type void, what will happen? The first layer will repeat. In the third layer also the repetition of the first layer will be coming. When you imagine the structure, you can see that the third layer, the repetition of first layer will be coming when you fill the C type void, isn't it? So, in 3-dimensional close packing we can see another type of close packing here. So, in this structure you can see that the basic layer, the first layer will be just as that of the hexagonal close packing that we seen in our 2D structure, 2D packing, isn't it? Yes. So, hexagonal close packing in the thottu mele layers varuna reethiyilana ee type. So, you consider here, then we can see that here 2 types of voids are there, A type void and B type void. So, you have 2 possibilities while forming the second layer. Which are they? Which are the 2 possibilities? Either we have to cover the A type void, either we have to cover the B type void, isn't it? So, covering both the void at a time is impossible. Okay. So, we have to cover either A or either A or B. So, now suppose I am covering the A type void here. So, just like this type of structure are getting. The dotted line indicates the second layer. So, the second layer you considered as the layer above this basic layer. Okay. So, A type void we filled here, then second layer will be the second row will be coming like this. So, in the second layer also will generate 2 types of void. We can name it as C type void and D type void. Okay. So, while forming the third layer we have also 2 possibilities. Either we have to cover the C void of the second layer, or we have to cover the D layer of the second void. Suppose we are covering the C type void of the second layer, then you will get a third layer. So, you can think that the third layer, when you cover the C type void of the second layer, you will get a third layer, and the third layer will be the just a repetition of the first layer, isn't it? So, we will get AB type pattern here when you cover the C-type void of the second layer, you will get a third layer with the repetition of the first layer itself. So, what type of structure you will get? AB type close packing in 3 dimension. AB type close packing in 3 dimension. Okay. So, while seeing this structure itself, we can see that this is more economic than 2 dimension, because we are trying to cover the most of the empty spaces, isn't it? So, here it is found to be 74%. The packing efficiency will be 74%. That is more economic than 2-dimensional close packing, right? Yes. So, what about the coordination number here? So, when you consider the central sphere, you can see that the number of neighboring spheres, when you count the number of neighboring sphere, you can't count here because it is a 2D structure. You have to imagine in a 3D manner. So, when you count the number of spheres, neighboring spheres, you can see that we have 12 neighboring spheres around a central sphere. So, what will be the coordination number? 12. So, in 3-dimensional close packing of this type, here the basic structure is like a hexagonal close packing. So, this is a 3-dimensional hexagonal close packing AB type. Here, what about the coordination number? So, when you see the central sphere, you can see that there are 12 number of surrounding sphere. You can't able to see here because it is a 2-dimensional board here. So, when you imagine this structure, you will see that we have a second layer, third layer, fourth layer, like that. So, when you consider any of the central sphere, you see that we have 12 number of neighboring spheres, right? So, we can say that the coordination number here is 12. And what about the packing efficiency? I told you this is more economic than the 2-dimensional, because we try to cover most of the empty spaces, right? So, here the packing efficiency will be 74%, right? Next, we move on to the next type of 3-dimensional close packing. Okay, just now I told you what is that? In forming the second layer, we can see that we have possibility of 2 other voids, that is C void and D void. Just now we covered the C void only. When you cover the C void, you can see that the third layer will be the repetition of the first layer. What about when you covering the D void? Just think about that. Just to imagine what will happen when you cover the D layer of the D void of the second layer. What will happen when you cover the D layer? You will see that the fourth layer will be the repetition of the first layer. While taking the bolts, you can do it in practice, right? Okay. So, when you cover the D void, you can see that the fourth layer will be the repetition of the first layer. What you see? Yes, the fourth layer will be the repetition of the first layer. So, how we call the other type? That is, here it is AB type, because third layer will be the repetition of the first layer. Here I told you in the third type, that is in the third type, what will happen? Fourth layer will be the repetition of the first layer. Okay, so you can call it as ABC type close packing. Okay, so you can see that the fourth layer will be the repetition of the first layer. Such type of packing is called cubic close packing. What is that? Cubic close packing. So, when you fill the or cover the D void of the second layer, you will get a packing, that is what we call cubic close packing. And what about the coordination number here? So, while considering the 3D view, you can see that when you consider the central sphere, the number of surrounding or neighboring spheres will be 12 here also. And here also the coordination number is 12, and packing efficiency will be same as that of the earlier model, that is the packing efficiency will be 74%, and it is known as cubic close packing. Okay. So, in 3-dimensional packing we have 3 types which are there. Simple cubic. Simple cubic means in 2D we saw that square close packing. Square close packing the mele layers above and below layers varumana nammal simple cubic close packing under, and there we found that the packing efficiency is only 52%, right? And the second type is hexagonal close packing in 3D. Hexagonal close packing, we see that we have 2 types of voids, and by filling the voids, first we will get AB type. Then the second possibility is the cubic close packing. That is what we can call it as here the fourth layer will be the repetition of the first layer. So we can call it as ABC ABC. Otherwise it is called ABC ABC type close packing. Okay. 3-dimensional close packing, we saw three different types of packing. Okay. In hexagonal close packing, you can see that there is a type of void present, C, D. Second layer I told you C, D voids are present here. And I redraw that C void here. What about the C void? Here the C void, 3 sphere, just above the 3 sphere, 1 sphere is coming. In the second layer, the 1 sphere is coming just above the C void. So suppose this void, while you considering this void, this is like a tetrahedral structure. So that is the structure of a tetrahedron, like this. This is what we call tetrahedron. Same like that of the void is coming here. So that is why this void is known as tetrahedral void. So this is present in 3-dimensional hexagonal close packing, right. So one more void, while forming the second layer, we can see that we have C type void and D type void. Okay. And in what is the speciality of D type void? While checking the picture, you will see that in D type void, the combination of two voids, that is the first layer void and second layer void and combination D void. Okay, so I'll redraw that void. Suppose this is the first layer, ഒരു കളർ കൊണ്ട് ഞാൻ ഫസ്റ്റ് ലെയർ കാണിച്ചു, the second layer next കളർ കൊണ്ടും കാണിച്ചു. അങ്ങനെ നോക്കുമ്പോൾ we will get a combination of the void here, and you can see that this is the joining of the two equilateral triangle, and you will get a shape like okay, hexagon. So this is, you will get a shape like octahedron. Okay. So while joining this two equilateral triangle, there is a combination void you will get, and while joining the centers of these 6 spheres, you will get a shape like a octahedron. So such type of voids are called octahedral voids. Okay. So next we will discuss one more close packing. That is another type of close packing, that is D, that is body centered close packing. So in body centered close packing, the first layer, the sphere will be drawn while keeping a small distance. We have to draw the spheres. In a body centered packing, we will draw the first layer in this manner. We are keeping small space in between the spheres, like that the first layer. And the second layer will be coming just above the space. Okay, like a body center. So body centered cubicle parna pole, the center and the second layer will be coming this center. Like that this pattern are arranged. Such type of packing is called body centered cubic close packing. Here the coordination number is found to be, 8, and packing efficiency will be 68%. Okay. So here the coordination number is 8 and the packing efficiency will be 68%. So these are the types of close packing in crystals. Okay. So today we discussed about close packing in solids. So we see that we have 1D, 2D and 3-dimensional close packing. Let's check the outview of today's class. Okay. So in 3D we have first type simple cubic close packing. 3-dimension is more important, that's why I am discussing in this manner. Okay. So simple cubic, first one. So the stacking pattern is AAA type pattern. Okay. So here the coordination number is 6 and packing efficiency 52.3%. And what is the type of unit cell present in simple cubic? You know, primitive. While taking the number of units per unit cell, number of particles per unit cell, I told you what are the types of cubic lattices. So here the unit cell present is primitive, and in the second type is body centered cubic. And here the stacking pattern is AB type, and also the coordination number here is 8, and packing efficiency is 68%, and here the unit cell present is body centered cubic, yes, BCC, we can call it as BCC. And the third type is hexagonal close packing in 3 dimension, hexagonal close packing. What is the type of stacking? Here's AB type, and here the coordination number is 12, packing efficiency is 74%, and what is the type of unit cell present here? Yes, hexagonal type, non-cubic hexagonal type. Okay. Then next is cubic close packing, cubic close packing. Here the pattern we can call it as ABC type. Okay. So, and the coordination number is 12 here, packing efficiency same as that of hexagonal close packing, that is 74%, and what about the unit cell present here? This is face centered cubic unit cell, that is FCC unit cell. Okay. So, now today these are the topic. So, next class we will discuss more about voids and what are the speciality or what are the types of voids. Okay. So, thank you.